Welcome back. So here, last class we have discussed about the power factor and all other remaining terms of the AC circuits, right? So I have seen about RMS value, we have seen about average value, amplitude, and some other important terms regarding this AC circuits. Okay. So today to begin, before beginning of this different pure AC circuits, let me introduce another phase difference between two sinusoidal waves. So we'll discuss that one. We'll move on to the next concept. So the phase difference of sinusoidal waveforms can be represented as below. So the generalized mathematical expression to define two sinusoidal quantities will be written as. So here, let me consider this V as a voltage and Vm is the maximum voltage and sinusoidal, this sine of omega t represent about its wave nature, right? So this particular sine of omega t tells about wave nature of that wave nature of that particular sinusoidal AC, right? Now, and if you let me consider similarly, let me consider this current I, that is at instantaneous current or instantaneous. These two are called as instantaneous voltage and instantaneous current. And we here Vm and Im are called as peak values. So these are peak values. Okay. So and here for the current, this part sine of omega t minus pi. Now this also represents about wave nature only, right? It tells about sinusoidal wave nature. Okay. Now here, if you want to see about the what is the exactly phase difference between these two AC quantities, so look at this first diagram. Okay, so this is called as a waveform nature, and this one is called as a phasor diagram. This one is phasor diagram, and this one is waveform diagram. Okay, waveform. Okay, now if you see this at time t is equal to 0, AC voltage AC voltage is at its amplitude is 0 here. At time t is equal to 0, its amplitude is 0. But at time t is equal to 0, current has a negative values. Current has negative value. At that time, voltage is at 0. Right now, as time goes, if you come at this point, exactly at this point, if you see at time t is equal to a certain time, maybe if you consider 2 seconds or 1 second, at a particular time, that time here current is at its amplitude is 0, but voltage has acquired a positive value. And if you go further to the next timing, so if you see at exactly peak value of voltage at this point, here voltage has acquired a maximum value, right? It has acquired a maximum value, but at that time, so our current has a certain amount of a positive value. So then if you go along with the time, that is omega t, so if you go along with the time, you can see that the voltage is leading than this current. So means where its current is lagging now by a certain amount of a phase, that is called as a phi, right? So you can see in this wave equations also, this voltage is given as a sine of omega t, and for current is given as sine of omega minus phi. So means this much of phase omega t is the and omega t minus phi. So these two are, we'll consider this one as a one phase, phase 1 is equal to omega t, and second phase is phase of a current. I'll consider this one as a omega t minus phi. So the difference between these two phi's is given by omega t minus omega t plus phi. So that becomes, so omega t cancels, then only the phase difference between them is 2. So that phase difference where current is lagging behind the voltage by the phase difference of phi. So that is represented with the wave phasor diagram like this. So if you consider this x-axis as a reference axis, where one will consider that as a phase with the omega t, right? So omega t will consider as a reference along with x-axis, where omega t minus pi, it is a minus phi, means phi amount is less compared to the x-axis. So that's why this current is drawn along this with a phi angle with respect to x-axis below this one, right? So here now, as current at voltage leads forward, that current is lagging now, right? Here current is lagging by the angle of phi. So that phase difference between two quantities is can be defined with the notation that is called as phi. So here you can understand which one is lagging and which one is leading. With respect to the voltage, current is lagging. With respect to the current, voltage is leading. So depending on the component, whatever we are using in AC circuits, in that case, whether voltage is leading or current is leading, that we need to decide by using the component which is using in that. So that we are going to study here. Those are called as single phase AC circuits. So that we will study here. They are called as single phase AC circuits. Okay, circuits. So these are single phase AC circuits. The three basic elements of any AC circuits are: first one is resistance, and second one is inductance, and third one is capacitance. As from the lower classes, you have already studied about what is exactly the resistance R, and what exactly the inductance L, and what exactly the capacitor C, right? So by using these three electrical components, almost all any AC circuit should be designed. So here, for the basic structures or basic circuits of this AC, we are going to study by using these R and R, L, and C. Okay. So there are three main phase, single phase AC circuits. That is, first one is purely resistive circuit, and purely inductive circuit, and third one is purely capacitive AC circuits. So these are the main three basic circuits of a single phase AC circuits. So if you study these three circuits, then we will come to know about the what exactly the phase difference between a particular individual component, that is resistance, inductance, and capacitance, and what are the effects of those three individual components on the AC circuit parameters, that is called as voltage and current. Okay. Now, first one, we are going to study about the purely resistive circuit. Okay. So this is what the circuit diagram of the purely resistive circuit, where we are this AC. This is called as a AC source. This one is as AC source, particularly AC. So AC is represented with this wave nature inside this circle. So this always represents about the source, that should be a AC one, right? So it should be AC one. Then here we have applied an initial input as a voltage, that is Vt is equal to Vm sin omega t. So here what V of Vt or V of t, we can write this one as a V of t also. So this is what is about. It is about instantaneous voltage. It is about instantaneous, okay, value. Instantaneous value, right? So here Vm is the peak value. So here we have used, that is one resistance is used in this circuit, where this resistance is connected series with the input voltage, that is Vm sin omega t. So now, as the circuit is completely closed one, we can apply Kirchhoff rules to calculate the current in this. So let me consider the current flowing at this instant of time in this circuit is IT. So otherwise I can call this one as I of t also, that is instantaneous current. And the drop across this resistance, whatever the voltage used by this resistance, I will call this one as a VR, where as I have explained here, this Vt is the instantaneous voltage, and Vm is the maximum voltage, and Vr is the voltage across the resistance which is used during the flow of the current. So that will create the current in this circuit. So we'll see what exactly the happens to the current in this circuit. So from the above circuit, we can have an equations for the voltage and current as below. Okay. So according to the Ohm's law, we have that the current IT is equal to Vt by R, where It and Vt are called as instantaneous voltage and instantaneous current. So instantaneous current across this circuit can be calculated as voltage divided by that resistance. This is according to the Ohm's law, right? So as Vt, we know that instantaneous voltage, that is equal to Vm into sin omega t divided by R. So Vm sin omega t is the instantaneous voltage total value, that is, right? So now if you calculate this one, as sin omega t is the only wave equation, that is, so other than this, Vm is the magnitude divided by R and sine of omega t, right? So now if you calculate this Vm by R, maximum voltage divided by that resistance, it actually gives about the current. So it actually gives about the current, that is called as Im, I can write. So from this calculation, we can write instantaneous current as It is equal to Im sine of omega t. So this represents over the instantaneous current at that time where the voltage drop is there across the resistance. From above equations, it is clear that the current is in phase with the voltage. If you compare this voltage, instantaneous voltage Vt is equal to Vm sine of omega t, then and if you compare the current, that is called as It is equal to Im sine of omega t. So whatever the result we got from this calculation is Vt is equal to Vm sin omega t and It is equal to Im sin omega t. So if you see the phases of these two, so both phases are omega t only. So there is no difference between these two phases. So means that current and voltage both are, we can call this one as in phase, right? So both are in phase for the purely resistive circuit. So purely resistive circuit. So in this you can observe this above circuit. There is no any other component other than resistance in this AC sourced circuit, right? So that's why it is called as a purely resistive circuit. And if we look at the exactly waveforms and phasor diagram of this particularly purely resistive circuit, we can see in these below, right? So sine wave and vector representation of instantaneous voltage and instantaneous current are given in this figure below. Okay, so this is a wave nature diagram. So this is a waveform diagram, and this is phasor diagram. Okay, phasor diagram. So you can see this where at the V of t means at the instant of where voltage starts, at that time only current will starts. Means at time t is equal to, at this here time t is equal to 0, voltage and current both are 0. And where when this voltage will become maximum, at that time only current is also maximum. And when current once again becomes 0, at that time only voltage is 0. So means at the same instant where voltage has a value, some certain value, like that only current will also have the same value. So these are called as in phase values, you can call, right? So from this only we can tell that both are in phase. So similarly, if you represent in the form of phasor diagram, if I consider a reference along x-axis where voltage, I will take voltage across resistance in the same x direction as a reference. Similarly, where current is not leading or lagging, that's why both as voltage and current both are moving at the same phase in across that resistance. That's why this current is also can be drawn along the same reference axis, that is x. As voltage moves with a certain angular velocity, that is omega, similarly current also moves with the same angular velocity omega. So there is no phase difference. So that's why both are in phase. So we can represent those in phase difference, or there is no phase difference, by using phasor diagrams. Okay, so this is what about a completely purely resistive circuit. And similarly, if you look at the power factor of this purely resistive circuit, the power factor is given by that is P F is equal to, that is cos phi, right? Cos phi, where this phi is called as phase difference, right? So phase difference. So in this purely resistive circuit, the phase difference between voltage and current is, that is phi is equal to 0. That's why the power factor of this purely resistive circuit will become unity. That is nothing but it becomes 1, as cos phi means cos phi is there. So if you take that phi value here, cos 0 is equal to, that is 1. So purely resistive circuit will give power factor as 1. So where power factor is nothing but it is the ratio of a true power to the apparent power. So that is what exactly the ratio of true power to the apparent power will be always 1 in this purely resistive circuit. Similarly, if you look at the purely inductive circuit, we can see in this circuit diagram, right? So here we have given the particularly input voltage as a AC source, that is Vt is equal to Vm sin omega t, as in case of the purely resistive circuit. And here, other than in place of the resistance, here we have used an inductor. So where L represents about the inductor. So this is inductive coil, right? So here only other than inductor we haven't used any other components of electrical circuits. So only source is there, and other than source only we have used particular inductor only. So voltage drop across this inductor is given by VL, as in case of a resistance we have used as a VR. So voltage drop across this VL is given by L inductor is given by VL. Then the current flowing at this in this circuit when the voltage is applied, that is called as the instantaneous current, that is called as IT, right? By applying the Kirchhoff law throughout this complete circuit, as a voltage is applied in this circuit. So if you look at this to the equation of the this purely inductive circuit, we get, as we have applied the voltage V of t is equal to Vm sin omega t in this circuit, right? So due to the self-inductance of the coil, there will be an EMF will be induced in it, right? So this back EMF will oppose the instantaneous rise of or fall of the current through the coil. It is given by EB is equal to minus L di by dt. So this is what by the self-inductance of that particular coil. As we know that the induced EMF induced in this inductance is given by is directly proportional to EMF induced in this inductor is directly proportional to the rate of a change of current flowing through this particular inductor, and it will be always directly proportional to this rate of change of current, and it is in the negative direction of the flow of the current, that in EMF will be induced in the negative direction, right? Or that rise or fall of that current in that particular inductor will be opposed by that back EMF, right? So now uh, uh, proportionality constant of this is given by EMF is directly proportional to minus of L into di by dt, where this L is a proportionality constant that is called as a self-inductance. Self-inductance, as there is only one coil here, there exists a self-inductance. So that EMF induced in this particular coil is given by E is equal to minus L di by dt. Here we are representing that one as a EB is equal to minus L di by dt, right? Now, as circuit does not contain any resistance, there is no ohmic drop. There is no resistance in this particular circuit. It is particularly purely inductive circuit, right? So there is no opposition offered by the resistive, that is ohmic drop. That is nothing but that is resistance. The ohmic drop means that is called as VR. There is no special drop of voltage due to the resistance here. So hence the applied voltage is equal to the equal and opposite to the back EMF. Whatever the EMF we have applied at the source, that will be always that should be equal to the drop across this particular inductor, right? So if you apply that equation here, the instantaneous voltage, that is whatever we have applied, that should be equal to the EMF of that particular EMF induced in that particular inductor. So as this is, if you apply the Kirchhoff loop here, so above, if you apply the Kirchhoff loop, that is V of t minus EB, that is EMF induced by this particular that is inductor, that is equal to actually 0. Then if you apply that, it becomes Vt is equal to EB. Here we have already defined as a negative because it is a opposite to the back EMF, right? So that's why we have written here as a negative. If you take Vt is equal to, so minus minus get cancels, only we get Vt is equal to L into di by dt. So as we know that instantaneous voltage is given by Vt is equal to Vm sin of omega t, right? Then that is equal to L di by dt. Now, if you separate all these components to calculate only di, so it becomes di is equal to Vm sin of omega t and into dt divided by L. Now, to get the particular instantaneous current for that applied voltage, we need to integrate on both sides. That we get, if you integrate this current at that di is a small current, then we get instantaneous current it. Then that is equal to Vm by L. Vm is a peak voltage and L inductance is also constant value. Then we need to integrate only sin omega t into dt. So if you integrate sin omega t dt, we get minus cos omega t divided by omega, right? Then if you rearrange that one, it is equal to instantaneous current is equal to minus Vm divided by omega L cos omega t. So we'll keep this cos omega t here only. So this becomes Vm by omega L. That is actually equal to that maximum current Im. So here Vm divided by omega L is equal to Im, that it tells about the maximum current in that instantaneous current. Then as here they have written that other than this Vm divided by omega L, we are only remained with minus cos omega t. So minus cos omega t can be replaced as minus cos of omega t can be replaced as sine of omega t minus 90. So sine of omega t minus 90 we can replace. So now here finally we get that one as it is equal to Im sine of omega t minus 90. Now if you compare both the equations, that is V of t instantaneous voltage, V of t is equal to that we have Vm of sine of omega t we have. Then I of t, that is instantaneous current, we have Im uh, into sine of omega t minus 5, right? So if you look at this particular expression here, current is lagging now because the phase difference between these two, phase difference, if I call this one as a phase 1 and this one I will call this one a phase 2, the phase difference between both is phi, that is phi 1 minus phi 2. If you get, that is equal to omega t minus of omega t minus of minus plus phi, that becomes phase difference is phi in this case. As here you can see that in case of a current, that phase is less amount of phi. So compared to this omega voltage, here it is less, means it is lagging on, as we have seen already in phase difference case. Okay. Here is another one important concept to we can observe here, that here we have written Im is equal to Vm divided by omega L, right? So here Vm is a peak value, we already know about it one, right? Peak value. So what about this omega L? What exactly it tells about? Omega L is nothing but if you see the Ohm's law, that I is equal to V by, that is resistance or opposition, V by R. So means if you compare these two equations, where omega L actually plays the role of a resistance, right? Resistance means that is nothing but a opposition offered by that particular component. In case of resistance, that we represent that one is a R, that is nothing but the opposition offered by that particular component. Now here we have a particular inductor L, right? So inductor L. So the opposition offered by this particular inductor is given by reactance. Reactance. So that we defined that one as a XL. The opposition offered by this particular inductor is called as a reactance, and that is equal to XL is equal to omega L, where this omega is nothing but a angular frequency and this L is nothing but the value of a inductor coil, that is nothing but inductance. Actually this phase difference in this case is exactly equal to 90, right? So this phase difference is exactly equal to 90 degree, means from these two equations exactly we get about that the current in the inductive coil or inductive circuit will lag by 90 degrees with respect to voltage, right? So otherwise another one sentence you can tell that this voltage is leading by 90 degree with respect to the current. So here we need to tell about the what we have calculated about the current. That's why that the current flowing in that particular inductor lags by 90 degree with respect to voltage. The current as it lags by the 90 degree, you can see that one in waveform and phasor diagrams. As this first one is a waveform diagram and the second one is a phasor diagram, right? So here we can see that as instantaneous voltage is given by Vt is equal to Vm sine of omega t, means where at time t is equal to 0 its value is 0, and time maximum it has a particular maximum value, then it becomes 0, then it becomes maximum as it is going with respect to original case. But in case of current, if you see this diagram, so as this one is sine of it is equal to Im into sine of omega t minus 90 degree, means it is getting lag by 90 degrees. 90 degree means actually we represented that one as a negative of cos. So negative of cos. Cos will be maximum at 0, but it is in negative direction, that it has a maximum value of a negative value at time t is equal to 0. As voltage is at 0, it is at a negative of its maximum. Hence there is a 90 degree of a phase difference where current is lagging, that voltage is leading. So if you see that the same thing in case of a phasor diagram, you can see here, as this one is, I will consider this one as the x-axis as a reference, where voltage is as it is there in the original case. But in case of current, if you see that one, it is 90 degree lagging behind. It is slower than the voltage by 90 degree. So that's why we call this one as a where current lags by pi by 2 or 90 degree with respect to the voltage in this purely inductive circuit. Now, if you see the same power factor of this particularly purely inductive circuit, power factor, power factor. So we get that when this power factor, we already know that this is equal to cos of phi, right? So here phi we got that one is equal to 90 degree. So therefore, the power factor of this particular purely inductive circuit is equal to 0, because cos 90 is equal to 0, as we already know. So here the ratio of actual power to the apparent power is actually 0 in this particular purely inductive circuit. And now, before going to the purely capacitive circuit, I will give some questions regarding this, whatever we have discussed till now from the beginning, as assignment questions. You need to submit those questions in Google Classroom, where we have given the particular link for that. So let me give some of the questions regarding this topic, whatever we have discussed now. So first one is define phase and phasor diagram. Explain more neatly. Explain. Okay. Then second question is, show that phase difference between voltage and voltage and current in purely inductive circuit is pi by 2. So it should be a qualitative one. So you need to derive this equation to show that there is a pi by 2 phase difference between voltage and current. So these two are the assignment questions you need to submit on a Google Classroom. So next class we are going to discuss about purely capacitive circuit and operator J. Then I am going to introduce about LCR series circuit. Thank you.